Welcome. In this lecture, we will talk about the discrete log problem and how it can be used for cryptography. So first, what's the definition of the discrete log problem? We assume that we have a group, and typically if we, like I deliberately use the term group here, which is a notion of abstract algebra, but we'll see down below that we can think of our prototypical group as being the invertible congruence classes modulo p. So if you don't know what a group is, think of it as z mod pz star for the rest of the lecture. Now, given a group and a base g, the discrete log problem is under the promise that a is a power of g, find that power, okay? Now, first of all, we want it to be hard to use it for cryptography, but it's not always hard depending on the group. So for example, in the case of g being the positive reals and then equipped with the multiplication, so what it means is we look at an a and a g that are in R plus, then the finding of x is easy. We should take this we just have to take the quotient of the logarithms, okay, of x and g, of a and g. Sorry for the typo. Now, a typical choice for the group is, like I said, z mod pz star, should be a star here, or the points of the group of points of an elliptic curve. Now, I will deliberately not talk about elliptic curves in this lecture, but everything that we say that, like I said, with the prototypical group z mod pz star, everything can apply, okay? In terms of the crypto, things will behave, the protocols that we describe will apply as well. Now, the first thing that has been, so the first crypto system that has been defined that leverages the hardness of the discrete log problem is the Diffie-Hellman key exchange protocol. So in this protocol, you have two players, Alice and Bob, and Alice and Bob want to create a shared secret over an insecure channel, so a channel that everybody can use and listen. And so there is a public G, a base, and a public group. Again, think of G as Z mod PZ star if you don't want to think of abstract groups. Then both Alice and Bob draw integers, and then they have G to the A and G to the B. So typically those integers are in fact going to be between 0 and the order of G minus 1, but this is a detail. Here, let's look at the high level picture here. We have that they draw G and A and G of B, they can compute these, and then they can send each other G and A and G of B. Now, if the discrete log problem is hard, somebody listening to this conversation, we hope, is not able to recover A and B. Now, each individually can compute G to the AB. Alice by raising Bob's value to the A, which she knows, and Bob by raising Alice's value to the B, which he knows. Now, the thing is, of course, so this protocol would be insecure if an adversary could recover G to the AB. Now, we hope certainly that the discrete log problem is hard, because otherwise the adversary could recover either B or A, and that enough plus the communication would allow the adversary to recover G to the AB. Now, in fact, Diffie-Hellman, the hardness of the breaking Diffie-Hellman might be not as hard, because in fact an adversary also have G to the AB. So what an adversary has is G to the A, G to the B, okay, and what they need to recover is G to the AB. So which is perhaps slightly weaker than having to recover B and A. Maybe the adversary will never learn B and A, but if they learn G to the AB, they win. But it's certainly necessary for discrete log to be hard. Now, the public key in the end is G to the AB. Now, one of the most obvious ways to attack the Diffie-Hellman protocol without having to solve the discrete log problem is the man-in-the-middle attack. So the man-in-the-middle attack assumes that on top of listening, the adversary can actually send messages. Now, if the adversary can be, so if such an adversary, which is active, is able to send messages to Bob and Alice, the adversary might pretend to be Alice talking to Bob and Bob talking to Alice. What it means is the adversary could perform independently two key exchange protocols with Alice and Bob. At the end, the adversary would share a key with Alice and share a key with Bob, and for example, could relay Alice's messages to Bob and vice versa and decrypt everything. So that is a big problem. That means that we need authentication on top of the properties of the Diffie-Hellman protocol. Now, with the discrete log problem, we can also do encryption. It is not typically used. What we use RSA is more popular, but there is a possibility to design an encryption scheme that leverages the hardness of the discrete log problem. And it's called ElGamal, after its creator, named after its creator. So we assume here that we have a G, a public group, a base in G, and then an H, which is, so what it means is it's a power of G. And so what is private, of course, is the particular power. And then the encryption, so given a message, we first pick a random Y and we define, we calculate G to the Y and H to the Y, which is S. And then the encryption is, so a vector with two coordinates. So one of them is G to the Y that's been created, and the other one is S times M. So the S that is created multiplied by M. So because S will look random, then we hope that S times M masks the message M. Okay, G to the Y is left here as a sort of hint for the person who's going to decrypt. Okay, because the person who will decrypt will not know why. All right, so how could they divide by S if they cannot recreate H to the Y? So we need to give them a hint about Y, but of course we can't just leave Y because otherwise everybody else can decrypt. Okay, so this G to the Y is going to be used by the person who decrypts. And so how do they do it? Well, they take this first coordinate, okay, we call that C1, and raise it to the power X. Okay, and that equals G to the Y to the X, which also is G to the X to the Y. And G to the X, remember, is H. So what it means is the person who does this is in fact able to recover H to the Y. Now they won't know what Y is, but that's okay, because once you have G, we have H to the Y, you have S, and you're able to divide the second coordinate of the ciphertext by S to recover M. Now, much like in the case of RSA, without any kind of clever random padding, there are major problems using this sort of textbook version as an encryption scheme. In fact, it won't pass a CCA2 security game, and I'm just gonna show real quick why. So assume you have an adversary and a challenger playing, and then the adversary, so the challenger, of course, is in charge of choosing the key material at random, and the challenger picks two messages, sends those messages, and then the challenger picks the random material that serves that can be used for the encryption, and then picks at random one of those two messages. So MB is the message that's been chosen to be encrypted. So G to the Y is calculated as part of the encryption process, and this is the ciphertext, and it's being sent to the adversary. Now the adversary can craft a new ciphertext, and that ciphertext is related to the ciphertext that has been sent, and then instead the only thing that changes is basically a second coordinate is multiplied by, for example, the inverse of M0. Okay, so what it means is we have a legitimate encryption here of MB, the message that was encrypted, times the inverse of M0. Now, the adversary sends it to the challenger. The challenger has to send the decryption. And then with that, of course, this is going to be either 1 if MB is M0, or it's going to be M1 over M0. But in each case, the adversary will be able to determine which message was encrypted. So this concludes this short video on how to use the discrete log problem in order to do cryptography. What we've seen is just key exchange and public key encryption. We leave out digital signatures for our next video that is dedicated entirely on digital signatures. Thank you very much for your attention.